Okay ra sa inyo, isahon lang nato ang exam ninyo, no? So, umano lang sa nato ang topic tanan, then we'll do um, an examination after mahuman ang tibok topic. Okay? Okay. Oh, oops. Start na. Start na. Okay. So, let's proceed to another topic. We have this momenta, generalized momenta. We can actually express the Euler-Lagrange equation in terms of momentum. Okay, so generalize momenta. We have this ignorable coordinate. So, dunay mga systems nga as you can see from the Euler-Lagrange. Okay, we call natay Euler-Lagrange nga ani, no? We recall the Euler-Lagrange is given by this qi is minus d dt partial L with respect to qi dot. Okay. So, dunay mga system nga dili siya dependent sa imong coordinate q. Like for example, free fall, um, ano, free particle. Ang free particle is wala siya potential energy. Dili siya function of x, only a function of velocity, right? So, we can actually express that into momentum. Okay? Kaning ato ang Euler-Lagrange in terms of that. So, take note for a free particle, okay, for a free particle, ang atong Lagrangian lang, for a free particle, the Lagrangian is just equal to only the kinetic energy, right? 1/2 m x dot quantity square. It's not a function not a function of x, position x, but a function of velocity. So in this case, the partial L with respect to x is 0, right? The partial L with respect to x is 0, and the d dt kani partial L partial of x dot is equal to mx dot. Sakto? Is equal to mx double dot. Okay? Or you can write this as, if di na ako sa i-derive, it is actually equal to this. Na ako'y d dt of mx dot lang. Okay? And then if you substitute this one to our Euler-Lagrange, it becomes this. Na ako'y minus d dt of mx dot equal to 0. And in this case, this mx dot siya is actually our momentum, right? This is our momentum. So, for a free particle, as you can see, for a free particle, if the derivative of this momentum, if the time derivative of this momentum is 0, it means that your mx dot is constant. Sakto? Because derivative of constant is 0. In this case, for a free particle, the mx dot here is a constant. So, doon na sa free particle, ang iyang momentum kay constant lang. Okay? Sa free fall, dili constant yung momentum. Sakto ba? Kaya kung nakoy object, ihulog din mo ang object. Okay? Ang may tabo is magkapaspas yung velocity, right? Magkapaspas yung velocity. So therefore, for a free particle, for a free falling bodies, not a free particle, no? Kaya siya kay free particle siya ang system. For free fall, the momentum is not constant. Okay? The momentum is not constant. But for a free particle, the momentum is constant based from the we derive it from the Lagrange equation of motion. Okay, so it is linearly depend. We call this one as the linear momentum. Okay, we call this one as the linear momentum px. Okay, linear momentum px. And again, for free particle, the linear momentum of your particle is constant. Okay. So, we can actually define, as you can see from the Euler-Lagrange, na we can define this. The linear momentum can be expressed as the partial of L with respect to x dot, which is equal to mx dot. Sakto ba? Based from this one, kani sa atong Euler-Lagrange, as you can see, kani siya is just equal to mx dot, sakto? Which is just our momentum, and I call that one as px, okay? I call that one as p sub x. So if I define p sub x as the partial L with respect to x dot, with respect to x dot as px, then uh, by definition, this is actually the linear momentum of the system. Okay, so in the case of in the case of generalized coordinate, we can generalize the momentum, linear momentum, in the case of generalized coordinates. We can generalize the momentum, linear momentum, as coordinates q1, q2, qn. Okay, we can generalize linear momentum as pk as partial of L with respect to q dot of k, where k runs from 1 to n. Okay? Where k runs from 1 to n. Depende kung saan coordinate mo gamit. So, pwede na akong ma-generalize ang momentum as this equation, partial derivative of our Lagrangian L with respect to its velocities, k, q, k dot. So, we call this one as the pk are actually called as the generalized momenta. Okay? Generalized momenta of your system. Okay? We call this one as generalized momenta of the system. So the Lagrange equation in terms of momentum, okay, can be expressed as this. In terms of momentum, in terms of momenta pk, momenta pk, okay, this is actually equal to this partial L with respect to kanino qk minus d dt of partial L with respect to qk dot, okay, equal to 0. And take note, ang nasa parenthesis can be expressed as pk. Okay, pwede na ako sa mas express as pk. So as you can see from that, makuha, if I transpose that one there sa pkas, na ako d dt of pk, okay, equal to partial L with respect to qk, and then take the time derivative of pk, you will get this pk dot equal to partial L with respect to qk. Okay, so please familiarize this one because um, pag maabot sa last na section sa kaninga chapter sa Hamilton's equation, magamit na to actually no kaning p dot. The p dot is partial L with respect to q, but I think instead of L, Lagrangian ato gamiton ni Hamilton's, okay, h, Hamiltonian equation h. So p dot k is equal to partial L with respect to k, because take note of this, based from ikan sa atong Euler-Lagrange na equation. Okay, so the p, tanawin mo no, pk is partial L with respect to q dot, tama ba? While the p dot k is partial L with respect to q. Okay, so there is this ignorable if your Lagrangian is not a function of q, is not a function of generalized coordinate q, then the pk dot is equal to 0. And it also means that your momentum is constant. Okay, kung 0 ni, so ito, if 0 ning pk dot, it means that pk is constant. Okay, pk is constant. The momentum is constant. And kano sa mag-0 ang imong p dot, it is when your Lagrangian is independent siya sa imong coordinate na q. Okay? So it is now readily apparent that if the Lagrangian does not explicitly contain the coordinate qk, then the pk dot is equal to 0. Okay? So muna na kung dili siya with this, akong L for example, dili siya or dili siya dependent sa akong q, then it means that your momentum is constant sa imong system. Okay? Say sa to ang sa free fall, no? Kung sa free fall, for example sa free fall, as you can see in free fall, the Lagrangian is equal to this one, no? 1/2 mx dot square minus mgx, sakto? Or if you use y, then pwede rin hapon na 1 half my dot square minus mgy. Same rin hapon na siya, no? So, in this case, your L is a function of x, okay? It is uh, dependent on x, okay? So, therefore, your momentum is not constant, okay? Your momentum is not constant. So, as you can see, if I have this Lagrangian, so for not free particle, no? For free fall, I have that. I can solve for p x, in this case, ang atong coordinate nga gamit is x. This is just equal to partial L with respect to, so ito, x, no? So, this is minus mg, sakto? Minus mg. So, therefore, p dot of x is equal to minus mg. And in this case, take note, if you do the derivative momentum, ang makuha mo is actually a force. Sakto? In this case, this is actually a force. Sakto? This is actually a force. Because take note from second law of motion, the dp dt is just equal to force F. Sakto? So if you take the derivative of momentum with respect to time, you can actually get a force. Although your force is constant, in this case of sa free fall, akong force is constant, but the momentum is not constant. Okay? The momentum is not constant. Okay? So this is your force. As you can see, P dot Px is minus mg. And then, atong Px nimo is just equal to sa itong Px na ko, partial L with respect to x dot. Sakto ba? Partial L with respect to x dot, and this is equal to, if you derive the Lagrangian with respect to x dot, you will get mx dot, which is just the momentum of your particle in the momentum of a freely falling bodies. Okay, so px is equal to mx dot, while p dot x is equal to minus mg. It's not a constant, but it varies. Okay, it varies with respect to time. Okay, so px is momentum, which is not a constant one. Ano di siya constant? Because take note, your L is a function of position x. Okay, so if wala siya function of x, ignorable coordinates, we call it as ignorable coordinates, then the momentum must be a constant. Okay, momentum must be constant. Sakto man mg, hmm, sakto na siguro na partial L with respect to x. EP uh, ADP dot okay, the momentum is not equal to that. Okay. And take note, mx dot here is not a constant. Okay. Okay. So, yeah. Say, for example, a pendulum attached to a movable support. So, I think kuha na to ni last time. Yan yung pendulum, not in an inclined plane, but kaning kuha lang, straight lang. Straight lang a plane. Say, example, oops. Itong example, marami kanino. I think kanino. This one. A pendulum attached to a movable support. I think we solved this one last time. Okay, and we know the Lagrangian of this system. I know the Lagrangian of this system. It is equal to this. So, oops. The Lagrangian of this one is equal to 1 half m plus mx dot square plus na siya rotation sa imong m nga kamay. So, doon na siya rotational kinetic energy equal to this 2x dot, and then na siya coupling kini cosine of theta plus mgr cosine of theta. Okay, so this is the Lagrangian. Again, we solved this one last time, and the Lagrangian is equal to this one. 1 half mx, okay, 2xr square theta, that's square 2x. Okay. So in this case, if you solve for the equation of motion, if I solve this one in terms of momentum, okay, if I solve this one in terms of momentum, I can write this, I can express the Euler-Lagrange into this. The equation of motion of this system is we have P, I think there are only two generalized coordinates. Tama ba? Alam ko ito, duha ka generalized coordinates, the x and the theta. Okay? The x and the theta. So this is equal to, if I solve the Lagrangian, the Euler-Lagrange in terms of x, I have this, right? P dot x. In terms of momentum, na ako d dt of partial of L with respect to x dot, which is equal to partial of L with respect to x. This is actually equal to 0. Manong 0 because, as you can see, your L is not a function of x, but a function only of x dot and theta dot. Okay? So, again, your momentum, the force, this is a force, right? P dot x, okay? P dot x, P dot is equal to 0. Okay? P dot is equal to 0. And then, the other one, with respect to theta, if you do the theta, P dot, with respect to theta, this is partial, this one, partial L with respect to x dot, theta dot, sorry, it's theta dot, oops, theta dot, okay, and this is equal to partial L with respect to theta, tama ba? Partial L with, this is theta dot, partial L. And from here, gikan ani with respect to theta, makakuha ko equation of motion equal to this one. Theta dot, di na ako solve, no? Makita na natin, no? Nasolve na po natin ni last time. X dot R cosine of theta plus G over R sine of theta equal to 0. Take note, your R here is constant. Okay? So, nakoy duha ka equation nga makuha in terms of theta double dot and in terms of x double dot. In this case, your P dot x is equal to 0. Your force, your x, in this case, kung imo ning i-dig in deeper, makakuha ka og x double dot ani equal to 0. Okay? X double dot ana equal to 0. Nganong gali 0, be? 0 ba ni? Murag 0 siguro ni, no? Nakoy 2x x 0 ba ito nasolve ba ni? Tanong ko, balik ko na po. Nasolve ba natin yung last time? Anyways, hindi na ako magkita. Sige lang. So, hindi na ako. Tirasun na ako eh. Okay? So, kana lang. Okay. With respect to theta, I can get this equation of motion for this one. If there's no x, as you can see, if there's no x here, if dili wala nag-move ang ako ang support, yan eh. Kung wala na naglihok, ang may tabo, the second term will be 0 and it will reduce to a simple pendulum. Okay? It will just reduce to a simple pendulum because your second term becomes 0 because your x double dot becomes 0. Wa man naglihok ako ang kani siya, no? Kani siya, kung di siya maglihok, then it's just a simple pendulum. Okay? Okay, so we have that, and then, yeah, we have that. When x dot equals 0, it is equal to, when x dot equal to 0, when x double dot equal to 0, then it will reduce to this, right? Partial, theta double dot, g over r sine of theta equal to 0, and this is just a simple pendulum. Okay? Simple pendulum. And then when theta double dot equal to 0, meaning wala naglihok si mass M, Then in this case, kung ang theta double dot nimo is 0, uh, unsay mahitabo, mura ra siya gana ra no. Mura siya gaingani ra no, na movable m, and then imuhang mass m is nagbitay lang no, wala siya naglihok. Okay, your theta is fixed there, it's not changing, wala siya nag swing, but mura siya og katong mura siya og airplane nga nagdala og kaning PC. I think na siya isa sa problem sa ko ano, physics olympiad no. Na kung na airplane moving at a constant speed, then nasa PC, unsay forma sa imong PC, ingani ba siya, straight ba siya, or ingani ba yung forma niya, ingani ba yung forma, bawag ba siya gamay, and so on. So this case, when your object is moving constant velocity, ang mahitabo is ingani lang siya, straight lang iyahang forma. Okay, so when your theta double dot is 0, then it means that your tangent theta, sakto ba? Tangent theta here is minus x double dot over g. Ganun tangent, okay, because of the sine over cosine. Ang mabili na lang man is ang second term o ang mabili na is kaning second term o ang third term. And if you solve for the theta there, it's just equal to minus x double dot over g. Okay? So, if dili ka gusto nga dili nimo ipalihok ang imong pendulum, so dapat i-take nimo ni nga kaning average minus x double dot over g. Okay? That's your theta. If you know, if we in this case, as you can see here, kaning equation, if we uniformly accelerate the support toward the right, the solution describes a pendulum that hangs motionless at an angle theta to the left of the vertical. So kung uniform ang acceleration, then dili mo lihok imong pendulum, ingani lang sa forma, no? Ingani lang sa forma. And to solve for the theta, to solve for the unsa ka slant ang imuhang PC, then it is just equal to minus x double dot over g. Okay? Minus x double dot over g. Di na siya muswing, no? Di na siya muswing. If take note, theta double dot is equal to 0. Okay? Yeah, that one. So that's pendulum attached to a movable support. Another example, what if I have a spherical pendulum? Unsay kalayan sa simple pendulum o spherical pendulum. Spherical is na siya spherical pendulum is doon na siya kani pendulum alam mo no, xy plane naman ang motion, two dimension lang imuhang motion sa simple pendulum, but for spherical doon na siya i-add nimo nga number i-add nimo nga variable fee para sa imong motion. So instead of mag-swing lang sa paana, pwede po siya mo swing paani, patubangan, more sa ingani no, na ako'y pendulum nag-swing sa paana, at the same time ga-swing po siya, di na ako ma-drawing, at the same time nag-swing po sa ingani. Okay, so ingani sa forma ito, oops, this one. Okay. This is the spherical pendulum. So dila sa two-dimensional but three-dimensional nga system. So instead of move lang siya on ZY plane, okay, move lang siya on ZY plane, gana lang siya, move po siya at XY plane. So mura siya butang nimo sa bowl ang object, okay, muna yung object nimo. So once you release it, move siya padulong dito, move siya diri, move po siya diri sa pikas ana. So move siya pa spherical, half sa sphere mo move mo hang particle. So mura siya gi-move sa bowl, okay, ni-move siya sa bowl. Okay, so ni-move siya sa bowl. So like that, ana na siya swing lang sa dra, and then so three-dimensional yung motion, but there is this force of constraint. Okay, so three-dimensional yung motion, no? So nasa originally I have 3 degrees of freedom, But since na ako'y isa ka equation of constraint, so ma-reduce siya into two generalized coordinates na lang. In this case, instead of three ka generalized coordinates, ang mahitabo because of force of constraints, duha na lang in terms of theta and in terms of phi. Okay? So in terms of theta and in terms of phi. Kung the force of constraint here is kaning L, tama ba? Kaning length of your string. Okay? The length of your string is your force of constraint. So the force of constraint here is x squared plus y squared plus z squared. Okay, so this is your force of constraint. So the generalized coordinate of this one is I have only two in terms of theta and in terms of phi. Okay, for simple pendulum, it's just in terms of theta, no? For simple pendulum, in terms of theta lang imuhang generalized coordinates. Okay? Okay, so for spherical pendulum, duha ka buok. So swing sa pana at the same time kay maglihok pud sa pa-phi nga direction. Okay, panana sa dito, no? Panana sa dito. Okay? So, what will be the equation of motion of this one? So, that's the problem. What will be the equation of motion? So, I have two generalized coordinates, so therefore I have two Euler-Lagrange equation. Okay? But first is we have to solve first the Lagrangian of the system. Okay? So, the Lagrangian of the system is given by this. I have two velocities. Okay, ako yung two velocities along theta and velocities along phi. I have velocity along theta which is equal to L theta dot, while velocity along phi is equal to L phi dot sine of theta. So these are the velocities, and my there is gravitational potential energy. Okay, there is gravitational potential energy. If this is, as you can see here, your mass m is located here. Okay, and as you can see, if you do, what will be the height of this mass m along from the ground? This is, if this is L, L mo na siya, no? Then this kaning ako ang kaning bracket is just equal to L minus L. No, it's L, gamay nga L, sorry. It's, if this is L, and then as you can see here, this one is L cosine of theta. L cosine of theta. Then the height of your M, kani imong height, H is equal to L minus L cosine of theta. Sakto? So, ang height sa imong H is, ang height sa imong M is L minus L cosine of theta. Okay? So, therefore, the gravitational potential energy is just equal to mg times H, where H is equal to L minus L cosine of theta. Okay. So, makuha na ko ang kinetic energy. Duha ka buki ang velocity, no? So, duha pud ka buki ang kinetic energy. Kinetic energy along theta, and then kinetic energy along phi. So, why is it that your B phi is L phi dot sine theta? Because, as you can see, if this is L cosine theta, then kani siya nga length, kana siya nga length is actually L sine of theta. Okay? That's L sine of theta. And take note, the velocity here is just the angular velocity. Sakto? And angular velocity is just equal to the length times the angular, the phi dot. Okay? So that's why na ko yung length. Ang length na ko is L sine of theta times the angular velocity, which is phi dot. In case of theta, na ko L theta dot lang because your length, ang length sa imong string is just equal to L. Sakto? The length of this string is just equal to L. So na ko L theta dot, ang iyahang with respect to theta, no? Ang iyahang velocity, linear velocity is just equal to the length of that string times the angular velocity theta dot. While for the phi, na velocity, I have length niya is L sine of theta. Kani siya nga length. Is L sine of theta. So therefore, B phi is equal to length, which is L sine of theta times the phi dot, or the angular velocity with respect to phi. Okay? So therefore, the Lagrangian is just equal to 1 half m duha ka buok kinetic energy no nakoy L theta dot square plus 1 half m L phi dot sine of theta square minus mg um, L minus L cosine of theta. So this is the Lagrangian of the system. If you simplify that, you will get 1 half m L square theta dot square plus phi dot square sine square of theta minus mgl 1 minus cosine of theta. Okay, so that's the Lagrangian. Okay, I want you to derive this one. Okay, using another method. Kung di ka kabalo, kung wala ka kabalo what is v theta and v phi, dali raman no? Kung galihok siya rotational, kung galihok siya in rotational motion, then always na siya angular velocity equal to theta dot and phi dot. Okay, so you can solve for the linear velocity with respect to theta and with respect to the phi. But I want you to solve the Lagrangian with respect to x, y, and z. Okay, so without knowing this one, okay, without knowing this, kabalo man ko nga naingani no kay garotate man siya rotation, garotate man siya ang iyang motion. Wala siya translational. Okay? Nganong wala siya translational because your L is fixed. Okay? Wala man siya niinat. So your L is fixed. That's your force of equation of constraint. So only ang imuhang kinetic energy is only the rotational kinetic energy with respect to theta and with respect to phi. So that's why doon na lang ko duha ka velocities ni ngani. But I want you to solve the Lagrangian if I solve this one with respect to x, y, and z. Okay? So parehas ra ba siya answer? Kung di ko kabalo o wala ko kabalo ani, okay, kung wala ko kabalo ana, pwede na ko sa solve with respect to x, with respect to y, and with respect to z. Okay, so that will be your assignment. In this case, your assignment will be this. Again, without knowing the v phi, which is equal to this, and the v, and the v data, which is equal to that, I want you to I want you to derive this expression of RL equal to that with simply kanilang concept in terms of Cartesian coordinate XYZ. Okay, so, so as you can see here, para dili ta take note ha, kung makakuha ko sa position sa akong M, then I can also solve for the velocity, sakto? So, let's start kaning una, nag-start ta diretso sa atong V, right? Nag-start ta diretso sa atong V. But if I start it from the position, okay, then I can solve for the velocity. And from velocity, ma-solve na ko si L or ma-derive na ko si L equal to this one. So derive, your assignment will be this. Derive L from, derive L, yeah. And you will start from the expression of the position of M. Of the position of M. Okay? Because if you know the position, if you know the position, you will know the velocity, you will know the velocity of M. Okay? So, in your assignment, you have to express your position R. Position R ba akong gamit? Your position R as nakoy x component I hat plus y component j hat plus z component k hat. And then, if you take the derivative of r dot and then square it, take note, this is the velocity, right? The velocity of m, sakto, of m. And if you take r dot square, because take note kinetic energy is 1/2 of the velocity square, of the speed square. R dot square is just equal to r dot r, sakto? R dot r. So if you take the dot product of your r, then you will get the velocity square, and then mo na imong ibutang sa imong kinetic energy, and from that ma-derive na ko si L equal to that. Okay? So first thing first is, what is the position vector M? Unsa ang position nako sa M with respect to x, y, and z? With respect to theta and phi, okay? I think nani sa inyong math phi ba tawag? Katong translating the Cartesian coordinate into spherical coordinates. Okay, so what is x, what is y, what is z in terms of r, theta, and phi. Okay, r, theta, and phi. That will be your position. And then take the derivative. If you take the derivative and then uh, get the dot product, okay, get the dot product, you will get the r dot square. You will get the r dot square. And then the kinetic energy will be equal to 1/2 m r dot square. I think the potential energy is dili siya mag-change. It's just mgl 1 minus cosine of theta. Only the 1/2 mr dot square ang inyong kuhaon. And then from that, makuha ninyo si Lagrangian equal to that one. Okay? So this will be your assignment. Assignment. So derive the L. Again, without knowing that there are two velocities. Okay, there are two velocities. Velocity along theta and velocity along p. You will start from the expression of the position, take the derivative of that, you will get the velocity, take the dot product of the velocity itself, you will get the r dot square, and then put that into our kinetic energy. You will get the kinetic energy minus the potential, you will get the Lagrangian. Okay? So, yeah. Print screen. Ako i-post na, ano? Post na ko daan kayo, makalimot na ko post. Okay. Okay, ito. Okay, so this is 20 points. Due is on Wednesday. Okay. Yeah, for a spherical pendulum, we have this Lagrangian equal to this, which is just a function of theta and phi. Okay, theta and phi. Okay, so once I have the Lagrangian, as you can see, I have the Lagrangian. I can now solve for the equation of motion. Okay, nakoy duha ka buok in terms of theta and in terms of phi. And as you can see from our L is not a function of phi, sakto? It is just a function of phi dot, but it is not a function of phi. So it means that from L, the expression of our L, phi is ignorable. Okay, we call this one as ignorable coordinates. Tama ba? Yeah, because L is not a function of phi. It's just a function of theta dot, and phi dot, not a function of phi. Okay, so we have phi is ignorable, and when you say ignorable phi, it means that the p phi, the momentum phi, is actually, you can write the momentum phi actually equal to this one. So, partial L with respect to phi dot, which is just equal to a constant. Again, if delete function of phi akong L, it means that the momentum of that in terms of phi must be constant. Must be a constant. Sakto? it must be a constant. Basta gali ignorable imong phi, dili function imong L with respect to phi, then P phi, the momentum phi is a constant momentum. Okay, so constant lang momentum along phi. Okay, so it is a constant, and as you can see here, ano ba ito? Because from the Euler-Lagrange, the partial with respect to phi is equal to 0. Tama? The partial with respect to phi is equal to 0. So therefore, the momentum must be a constant. So if you do the derivative of L with respect to phi dot, what we will get here is kanilang second term, no? Akong makuha is kanilang second term, which is equal to P phi, which is equal to ML square phi dot sine square of theta. Again, this is just a constant. And as you can see, the momentum is constant. The momentum along phi is constant. As you can see here, this is just equal to the angular momentum about the vertical axis. Okay, this is the angular momentum about the vertical or the z-axis. Okay, so or the z-axis. Tama ba? Because take note, angular momentum is defined as mv cross r. Sakto? Okay. Tama ba? The angular momentum is defined as mvr. Dili L ako gamit. P phi na lang. Phi. So as you can see, P phi, the angular momentum is v phi cross r. Okay. As you can see, the v phi is given. Itong phi direct L theta dot sin theta. Okay. So na ko M. The v phi is L theta dot sine of theta. And your r here is the length of kaning length, not the L, but kaning length. Okay, kaning length is L sine of theta. So times L sine of theta, you will get is ml square theta dot sine square theta. Okay, so the angular momentum about the vertical axis is equal to ml square theta dot phi dot sine square of theta, which is, take note, a constant function. Okay, the angular momentum along about the vertical axis is a constant. Okay, it is a constant. Now, that's for phi. What about for theta? So what about for theta? We have this, right? For theta, the Euler-Lagrange is given by this partial with respect to theta that equal to partial L with respect to theta. And if you do the math, if you derive this one, if you derive the L, you will get this m L square theta dot square equal to ml square phi dot square sine cos sine theta cosine of theta minus mg L sine of theta. Okay, if I let s equals phi dot sine square of theta equal to p phi over ml square. Sakto? P phi over ml square. This is based from this one. Okay? Uh, if I solve for theta ml p over ml square, as you can see, p phi over ml square is just equal to phi dot sine square theta. Okay? So the phi dot sine square theta is just phi pi over ml square. Okay? Phi pi over ml square. So if I let s as that, I think kani nga term, wala na. Anyways, if I define S as the angular momentum over ml square, okay, over ml square, then um, the kani nga term becomes this. Then equation 1 becomes then 1 becomes theta double dot plus g over L sine of theta minus s square cosine of theta over sine cube of theta equal to 0. Okay? Again, when I define S as pi dot sine square theta, kani sa diri dapit, nasa diri dapit, kani dapit mga term diri, kani. Okay? Nasa diri ang term. Then this becomes theta of theta double dot plus g over L sine theta minus S square cosine theta over sine cube theta equals 0. And I think this two terms are familiar. Okay, kani siya is actually equation of motion of a simple pendulum. Sakto? The theta double dot plus g over L sine theta is an equation of motion for a simple pendulum. So when phi is equal to 0, oops, okay. When so this case one, again this is ang spherical pendulum is a generalized simple pendulum, no? So na siya motion along phi and motion along theta. Case 1 is when phi is constant. When phi is constant, what will happen? Kung ang phi kay constant, the phi dot equals to 0, therefore S is equal to 0. Sakto? So therefore, it will reduce to only these two terms, G over L sine of theta equal to 0. Again, this one is a familiar equation. This is an equation for simple pendulum. Okay? So, when phi is constant, of course, dili siya mulihok lang sa paana lang, no? With respect to theta lang. So, it's just a simple pendulum. Kaya phi is constant, dili naman siya mulihok with respect to phi. Okay, so we reduce the equation of motion to a simple pendulum. For case 2, okay, case 2, when we call this one as conical pendulum. Okay, conical pendulum. Conical pendulum. When theta is constant. When theta is constant, what will happen? Theta dot is 0, and of course, theta double dot is also equal to 0. So your equation becomes this, G over L sine of theta minus S squared. So mawala itong theta double dot, no? Cosine of theta sine cube of theta equal to 0. And if you solve for the S square here, if you solve for the S square here, S square is equal to G over L sine to the fourth of theta, second of theta, and then the theta dot square, the velocity, not theta but phi, so it's phi dot square, because take note S is defined as S is equal to phi dot sine square theta, so therefore when you have S square, then it is equal to phi dot square sine to the fourth of theta. Okay, sine to the fourth of theta. So we have phi dot square is G over L sine to the fourth of theta over sine to the fourth of theta second of theta. So therefore sine phi dot is equal to G over L second of theta. And if you graph this one, the graph is actually a conical pendulum. Okay, conical pendulum. So ang may tabo, instead of ang iyahang motion is this, na ako'y mass, mulihok lang sa pana lang dayon. Pana lang yung motion, no? Pero di siya mag-swing, maglihok lang sa pana. So that's why gitawag siya conical pendulum, because ang form, ang shape ngayang forma is a conical shape. Okay? So instead of swinging, magana yung pag-swing, when theta is constant, ang metabo is mutuyok lang sa pana. Okay? So conical, we call it one as conical pendulum. Okay? So mulihok. Ano man ang, this is simple pendulum. Conical pendulum is this. Okay? This is conical pendulum. And if you combine the two, mana siya, tapos mana na po, mana siya, that is spherical pendulum. Okay? This is spherical pendulum. So, conical, simple pendulum, conical pendulum, and then spherical pendulum is combination of the two. Okay? Combination of the two. Okay? And that's it. Yeah, that's it. Yeah, next meeting. Do you have any question? Allow me question. Next week, next meeting, we will have this Lagrange multiplier. So what if we will uh, take note, uh, last time is we know the equation of constraints, and then we consider that one before solving the Lagrange. We consider the equation of constraints. In this one, what if dili nato i-consider ang we'll add this so-called Lagrange multiplier sa atong Euler-Lagrange equation and then solve for the equation of motion. Ang tanong to, pares na sila o answer, no? Pares na sila answer actually. Uh, Tungagan lang nato what will be the Lagrange multiplier so-called lambda. Okay. So how to solve for the lambda here. That will be our topic next meeting. The forces of constraints or the so-called Lagrange multiplier.